Okay, so today for our experiment, we'll be looking into an experiment called asynchronous and synchronous counters. So I think all of you are very much aware as to what's a counter, isn't it? Can someone tell me what's a counter? You can unmute and respond. What's a counter?
It's a collection of flip-flops which counts.
Okay, can you tell me some applications of this?
They are used in stopwatches.
Stopwatches, okay, and then okay, just to recall a few concepts. Okay, counters are examples of registers. Okay, as one of your friends suggested, they will count a sequence. We can program a counter to count in a specific way that we wish to. Okay, and sometimes it's also called as pattern generator because we can generate a certain pattern, or we can make the counter go in a particular sequence as we wish to, or how we program it. Okay, each stored 0 1 combination is called state of the counter. Fine. So I think you're very much aware of the state diagram. You're very much aware of the state tables, right? The transition tables, isn't it? Are you all aware of these concepts?
Yes, sir.
Okay. So can someone tell me how do we get a characteristic table?
For which flip-flop, sir?
Any flip-flop, how do we obtain a characteristic table?
We will give input and the present state will consider as input and the next
Mhm.
state is output.
Okay. So which means you are making use of your truth table, isn't it?
Yes, sir.
With the help of truth table, you are proceeding to find out something called characteristic table, right? Okay. So now based on these concepts, okay, we will just move on. Of course, there's another point. If a counter has m distinct states, then it's called a mod m counter. Okay. So the number of states represents this mod uh, m. Okay. So suppose I say mod 6, then it would have 6 states. I say mod 10, then it would be a 10 state counter. So the order in which they appear is called a sequence, and that is called a counting sequence. Okay. So we can represent this in the form of a diagram. Okay, and that is nothing but called a state diagram. Okay, so I have picked up this information from your prescribed textbook, which is given. Okay, so let us say you have state 1, and then you're moving into state 2, state 3, state 4, and similarly state m. So we are generating a sequence in which these states are to move one after the other. Okay, so that's called a state diagram of a counter. Now, as you all know, there are two types of counters, synchronous and asynchronous. Can you tell me the difference between them?
In synchronous counters, all the clock terminals are connected to a single clock source.
Correct?
And in asynchronous, the clock of the next flip-flop is connected to the previous output of the flip-flop.
Very good. Very good. So we are connecting the output. So which means it is actually dependent on the previous flip-flop, right? In asynchronous. But then in synchronous, that's not the case, isn't it? We are looking into uh, a single clock driving all the flip-flops. Fine. So here you have modulus 2n, where n is the number of flip-flops in the counter. So similarly, we can have binary up counter and binary down counter. So even this is for your syllabus, okay, for your lab, where you have to design an up counter and a down counter. So I think counter design by now, all of you are very much aware, isn't it? Yes or no?
Yes, sir.
You will
Yes,
need,
sir.
yeah, you will need the excitation table, right? How do you get the excitation table? From characteristic table. How do you get the characteristic table? From your truth table, right? So once you know all of this for a particular flip-flop, then accordingly you can proceed. So just have a look at this diagram. Of course, this is not for your lab point of view, but this is just for your understanding. So this is a type of asynchronous circuit where the clock of the next flip-flop is actually driven by the output of your previous flip-flop. Okay, so this is actually connected to the previous output. Okay, so the clock is driven. So what is the importance of a clock? Is clock so necessary in a circuit?
It will tell the flip-flop to move from previous state to next state.
Next state, and also it will activate the flip-flop, isn't it? So it's like the on and switch off for a circuitry, right? So this is going to be your asynchronous type where the clocks are driven, the subsequent flip-flop clocks are driven by the previous outputs. Fine. So now when we talk about the synchronous type, okay, just a moment. Okay. So in synchronous, the most important thing is the count pulses are directly applied to the control inputs, which is C of all the clocked flip-flops. So here, all the flip-flops change simultaneously. That's important. Okay, it is not waiting for the previous flip-flop. All the flip-flops change simultaneously after the appropriate propagation delay associated with a single flip-flop. Right. So this is important. Right. So we are looking at flip-flops wherein they are actually uh, uh, changing simultaneously, isn't it? Okay, so this is nothing but your synchronous. So for your lab point of view, okay, we will be just looking at a simple circuit, okay, a simple IC, and then we will move on. So just for your reference, okay, you can have a look at this. In the previous configuration, we saw that these clocks were uh, driven by the previous output. But here we see that it is just connected to the same clock pulse, just like your first flip-flop, right? So which means as soon as I give a clock here, as soon as I give a clock, then uh, immediately, okay, I can see changes in all of these flip-flops. So which means my Q0, Q1, Q2, and Q3, everywhere changes will be reflected at the same clock pulse. Of course, there's going to be a slight delay, which is associated with each flip-flop. But then comparatively, when you compare with your asynchronous type of flip-flops, here the changes are going to be spontaneous. Okay. So I think now you are very much aware as to what is a synchronous and asynchronous counter. Is it clear, all of you? Any doubts, please feel free to ask. Yes. Can I move forward?
Sir, this
Yes, sir.
mod M is there, no, sir?
Huh, huh.
If it is mod 7, it will count from 0 to 7 or 0 to 6.
It is states, number of states. Okay.
Okay.
So if you start from 1, then it is going to be 7. If you start from 0, then it's going to be 6. How many states?
Okay.
That's it.
Okay.
See, that's why I showed you this diagram. Yeah. See, that's why I showed you this diagram. So how many states you have? Okay, that is going to be the number of that's going to be the number in the mod,
Okay, sir.
right? Some reason it's too buggy. So just a moment. Okay. I just wanted to show you that point. Yeah, see, this is the important point which you have to make note of. Okay, if a counter has m distinct states, then it is called a mod m counter. So it's only dependent on the number of states. You understood, right?
Yes, sir.
Yeah. Okay. So it depends on from where you're starting, and you know, many times that causes a confusion when you're starting from zero, right? Okay. Just a quick glance at mod m. So mod m counter. So m, where m is less than 2 raised to n. Of course. Right. So let us say a mod 10 counter. Okay. So here it's not that it's going to count till 10. Okay. It's just that it's going to have 10 states. See, you have from 0 to 9, and after 9 it's again going back to what? The initial state, which is 0. Understood?
Yes, sir.
Yeah. So in this state, see, now it's looking for a q0 to be high and q3 to be high. So q0 and q3 both are connected to the AND gate, and only if both are high, then only there will be a 1 here. So if it's a 1, then load. So load means what? 0 will immediately start getting into, or 0 will parallelly get into D0, D1, D2, D3. And then the count starts. Because see, we do not have Q3 and Q0 to be 1 anywhere else, right? So this is the only state. This is the only state where I have both Q3, both Q3 and Q0 to be high, right? In the other states, it's just that one of them is low and the other one is high, right? So what I will do, I will connect these Q0 and Q3 because I'm interested in the high values of Q0 and Q3, right? So once Q0 and Q3 is high, okay, then I will get a 1 here, so which means load is activated. So once load is activated, then 0 gets into D0, D1, D2, and D3. Is that clear? So which means right after this, it's starting off with 0. Understood? Yes?
Yes, sir.
Yeah. So if you count, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 states. Okay. So that is nothing but called your mod 10 counter. Is that clear, all of you?
Yes, sir.
Okay.
Yes, sir.
So now let us actually get into your lab. Uh, now that you know how to differentiate, between synchronous and asynchronous, we'll just have a look at it. We're just going to study some part of it. Okay, of course, we're not going to look into the whole experiment today. Uh, just a few section of it. Okay. So today we are going to look into realization of 3-bit counter as a sequential circuit and mod n counter. Okay, so we are going to make use of the ICs 7476, 7490, 74192, and 74193. Right. So for our asynchronous counter, so we use the IC 7476, the first one. Okay. So asynchronous, I think now you know the meaning, right? So which means the outputs are uh, connected to the next subsequent flip-flops. So this is your block diagram having different terminals. This is made up of JK flip-flop, okay, and it has J0, K0, J1, K1, okay, and it has this should be J2, and K2 also should be somewhere here. Okay, so there is some typo error. Fine. So JK flip-flops are employed here, and you have your VCC, and then you have your ground. Okay, then you have your preset and your clear values. Okay, so preset means we are setting the value, all the values of the output to 1. So here this is active low concept. Okay, so which means we have seen in our previous experiments, right? Active low means the opposite thing happens, isn't it? If I give a 0, then 1 comes in. If I give a 1, then 0 comes in, right? So accordingly, this is your mode select table. So which means when my preset is 0, this is as good as a truth table for your IC 7476. Okay. So when a preset is 0 and clear is 1, you have all the ones at your outputs. Okay, and this mode is called preset. So which means I am setting the value. Set means 1. Next, when the preset is 1 and clear is 0, then it means I am giving 0. Okay, so that is called a clear mode. So which means whatever values are there in the IC, those values are getting cleared off, because we do not want any junk value to come as output. You're following, right, all of you? Yes?
Yes, sir.
Okay, fine. Accordingly, when you have 1 and 1 both, then whatever is in the memory, the same thing will remain, which means there is no change at all. When all goes high, okay, when your control, when you clear and preset, okay, so when you give all of this high, then uh, you will have the counting sequence started. Okay. So that is when the counter will actually start its function. So this is the representation 7476, and you have your Q naught. This is just like your shift registers. Remember SIPO and SISO, serial in, serial out, right? The same fashion you can actually consider. So you have your Q naught here, Q1 and Q2, and then you have your preset values, the clock values. Now see, clock is only given to the initial flip-flop, right? To the initial stage, right? The next stages are all driven by the previous output. right? So this clock is driven by the previous output. Similarly, you'll be obtaining your values, which is Q0, Q1, and Q2. And um, yeah, so that's about it. The values, the asynchronous mode of operation. Now, when you look at the truth table, okay, so you can see that the counting starts from 0, 1, 2, 3, 4, 5, 6, 7, right? So this is as good as, increment by 1. So as your clock keeps going forward, so you will have to wait for the outputs of the previous state, because that is going to drive uh, the values into the next flip-flop. So I think in our next lab, we will look into decade counter, which means it should be able to count about 10 sequences. Okay. So we will see how Q1, Q2, Q3, okay, and how the clocks, how the reset values are all connected, and how we start getting the values. So we will look into it probably in our upcoming labs. Okay. So in this concept, do you have any doubt as to how this is connected and how we get this going? Any doubts, students, with this?
No, sir.
Okay, fine then. So I will be sharing in some more information with you guys. Okay, keep track with Google Classroom, and you'll be able to have updates on it. Okay, so should we end the meeting now? If in case any doubts, then feel free to ask us on the classroom. Okay, we will have another meeting. Is that
So
fine? All of
this
you?
week's observation up to
Mm.
here we have to raise, sir.
Yeah, yeah. You can write it up to here in
Okay,
the
sir.
truth table. Fine. I'll
Okay,
be
sir.
sending it. I'll be sending it. Right?
Yes, sir.
Okay.
Okay, sir.
Yeah.
Thank you, sir.
Okay.